All right, let's get started. Well, good afternoon, everybody. This is Arun Thiraviam, and I am a simulation product specialist with GoEngineer. Um, Thank you for joining us this morning for a presentation on the structural analysis tools that's integrated in SolidWorks called SolidWorks Simulation. I'm going to try and attempt to go over a couple of cases where I've taken advantage of two-dimensional geometry to actually run analyses, and hence the presentation is titled Simulating in Two Dimensions. Now, before I get started, there are a couple of housekeeping items I want to get out of the way. You guys have been muted. Will remain muted for the remainder of the presentation. At the end of the presentation, we'll leave the floor open for questions. The presentation link will be sent out to everybody, so it will be available for you to replay. And finally, if you guys have a Twitter account, um, please don't hesitate to live tweet any quick tips that you pick up from the webinar. Uh, Try adding a hashtag GoEngineer, and please tag the GoEngineer Twitter account as well. And like I said, following the presentation, there'll be some time for questions. All right, let's get started. So as far as structural analysis goes, we are typically faced with parts and assemblies that we need to test for structural integrity. For instance, this little picture that you see on screen is essentially from a link and sprocket assembly. So you have this little gear that makes certain revolutions at a certain speed. You want to see for every revolution how uh, this cantilevered link behaves, and you know what the stress distribution on the cantilever beam is, as or the cantilever link is, as the little gear makes one revolution. So just to give you a snapshot of what this analysis looks like, it's SolidWorks simulation. So you notice as the link slips through one tooth, the cantilever portion of the link kind of deflects, and you're able to see the stress distribution with the variation in with the motion of the gear. So this is a sort of a complicated analysis. We call this the nonlinear static analysis. Nonlinear because the analysis takes place in many steps, and as the shape of the link changes, so does its stiffness, and the contact between the link and the gear also changes. So in order to keep track of those changes in contact conditions and the shape change in the link, we need to run a nonlinear analysis. And a static analysis because the speed of the sprocket doesn't really matter. It's only uh, trying to figure out at different states of the sprocket's rotation what is the deflection on this little link. So you can imagine that this is a complicated analysis that may take many steps to run, and having a lot of elements and having a lot of geometric anomalies is not going to help. Now, how this analysis was run was that this three-dimensional geometry was reduced to two-dimensional geometry to save time. Now, it's not always about saving time. We need to find a balance between saving time and running accurate analyses. So during this presentation, I'm going to talk to you about a couple of techniques or a couple of, I guess, indicators by which you can decide how whether or not you can boil down your three-dimensional geometry and just run on the two-dimensional geometry. Now, again, to set up a little agenda for the presentation, now with two-dimensional analysis, we are attempting to speeden up the finite element analysis process. As far as two-dimensional simplifications go, in the structural analysis context, there are essentially three modes. I'd like to go over those three modes as well. And as always, it's nice to have some kind of hand calculations to back up these simplifications just to make sure you're not sacrificing too much of the accuracy for time. Great. Now, speaking of the three modes, as far as simplifying three-dimensional geometry to two-dimensional geometry in structural analysis goes, there are three cases: the plane stress, the plane strain, and the axis symmetry. Essentially, each of these cases are used for uh, different kinds of geometry based on how the geometry is generated. For instance, the plane stress and the plane strain cases are utilized for extruded geometry, where you have the cross section drawn out as a sketch and you extrude it for different distances. And the axis symmetry simplification is essentially used for revolved geometry, where you draw a sketch, indicate an axis, and you revolve the sketch about the axis to generate the solid geometry. Now let's talk about the plane stress case. What's so peculiar about the plane stress case? Now, when you take a finite element analysis, it's essentially a three-step process. You start off with modeling the geometry, then you apply the loads, boundary conditions, then you mesh the geometry, and finally you run the analysis and you get these kind of rainbow plots indicating the stress distribution of your geometry and the displacement and the strain. Now, under the hood, what is actually happening is uh, with the with inputs such as forces, the geometry of the design, and the material properties that make up the design. Uh, the solver essentially utilizes all these inputs to first figure out the displacement field. Now, after it figures out the displacements, it figures out the percentage of deformation, which is also known as strain. And then finally, using this strain, it figures out the stress distribution. So you start off with the forces and the boundary conditions. Utilizing these boundary conditions, the displacement field is figured out through stiffness matrices. And using the displacement field, there are relationships between uh, how each nodes in your finite element model displaces and what is the associated strain with those displacements. Now, after the strain is figured out, well, stress is proportional to strain. Maintaining that proportionality, the stress distribution is figured out. So this is essentially the process, and the equations that essentially govern this process are called constitutive equations. Uh, just to give you a snapshot of what the stress-strain relationship looks like in this constitutive uh, equation, let's assume a cube from the geometry being analyzed. Now you pull out this cube and you apply a load on this cube. What happens is it undergoes two distinct states of stress, the shear stress and the longitudinal stress. Now, as far as the shear stress goes, there are three components, and as far as the longitudinal stresses go, there are three components as well. So there are totally a set of 6 component stresses that the software is going to use to give you an equivalent stress that then you compare versus your yield to justify the structural strength of your geometry. Now, this little stress calculation process involves the processing of this, big old matrix. Now, what this matrix relates is all of these stress terms to all of these strain terms. In other words, each of these stress terms is actually dependent on each of these strain terms, and this dependency is maintained by material properties such as the elastic modulus of the material and the Poisson's ratio. Now, what we're proposing what uh, engineers propose uh, planes with the plane stress configuration is that let's assume a configuration where you have 0 out of plane stresses. Now, assuming 0 out of plane stresses kind of simplifies this matrix and it speeds up the stress calculation. Now, although in theory it's easy to make these simplifications, now these simplifications need to manifest as geometry. So to talk about the kind of geometry that can actually utilize these simplifications, it's essentially thin geometry. So anything that's thin, as indicated by this plate or the spanner, can be assumed to exhibit these 0 out of plane stresses. There are no stresses in the z direction. So eliminating all those terms enables you to speed up the calculation, and also from a geometric standpoint, you don't have to run an analysis and mesh the thickness. It's enough if you run the analysis on just the surface or on just the two-dimensional sketch that was used to generate the three-dimensional geometry. Now, how about plane strain? Now, while plane stresses are good for thin geometry, now plane strain are good for geometry that have infinite extrusion distance, where the extrusion distance is, uh, you know, many orders of magnitude higher than the dimensions of the cross section itself. For instance, beams. Um, so a lot of beams have constant cross sections extruded through large distances. In order to study the in-plane behavior of the beam, you really do not have to model the entire length of the beam. It's enough if you actually just took the cross section and you ran an analysis on it. Now, with the 0 out of plane strains, the assumption is that the length of this is so great, or the extrusion distance is so great, any small amount of strain that's developed by virtue of these in-plane stressing um, is essentially ignored, is tends to zero. So the geometries assume that not to stretch or deflect, in the z direction. So again, talking about the constitutive equation that breaks down the stress calculation equations by by a couple of terms, and also um, you're you're able to run the analysis on just the sketch. A couple of examples of this case would be, a dam subjected to a horizontal load. It's enough if you actually just model uh, like I said, the cross section of the dam without actually having to model the extrusion or the 3D geometry. Another example would be a pipe subjected to external pressure on its surface. Now, one key factor behind running the plane stress and the plane strain configurations is that you need to make sure all your stresses or all the forces that's applied on the model is in plane. There aren't any out of plane forces because the inherent assumption is there is no out of plane response. And finally, axis symmetric, a little more straightforward to understand. Uh, the the basic condition to run axis symmetric configurations is that the loads, the constraints, and the geometry need to be axis symmetric. For instance, in the case of this pressure vessel, uh, the it's a big metallic balloon. You'd like to see by virtue of an internal pressure how this metal pressure vessel expands. You don't have to run the analysis on the entire pressure vessel. It's enough if you extract the 2D geometry that was used to that was revolved around the axis in order to generate the pressure vessel itself. So that's a case where you'd use axis symmetric. Now, in order to kind of demonstrate this, how you set up a two-dimensional analysis, and what are the kind of results you get from the analysis, I've taken this example of a crane hook. Now, with this crane hook, it has there are there are two areas of peculiarity with this crane hook. The first area is that it has a constant cross section, so uh, it has a thickness of about 0.75 inches. Now, the second area is that the crane hook is similar to or is considered as a curved beam. So a lot of the concepts that go into hand calculating the the stress distribution on the beam or the behavior of the beam can be applied to this curved beam condition. So what I'm going to do is I'm going to jump into SolidWorks and run an analysis on this little crane hook. So if you can see, the boundary condition is that there's a 5,000 pound load acting on the curved surface of the crane hook. Now the goal would be to measure the stress distribution across this section and to kind of compare the results you get from SolidWorks and hand calculations. Okay, great. So let's jump into SolidWorks. I have the software already open. I'm going to grab the crane hook that I've modeled based on the geometry indicated in the slide. So I have a little sketch now. The outer radius of the crane hook being 6 inches and the inner radius being 2, and thickness of the cross section being about 4 inches. Now I have these split lines created because I I regard these areas as critical, and at the end of the analysis I like to study the stress distribution across these areas so that when I do run the hand calculations I have something to compare against, and also I could use these sections to essentially validate the structural strength of the beam. Now, as far as running an analysis goes, with SOLIDWORKS Simulation is completely integrated into the CAD tool. So jumping into the Add-ins tab and grabbing the SOLIDWORKS Simulation button gives you access to all the analyses you can run under this window. To access different analysis types, I'm going to jump into the Simulation tab, expand the Study Advisor, and hit New Study. Now, based on my subscription level, I have a buffet of studies that I can use to set up or test virtually the performance of this design. So I'm going to start off with just a static analysis because I'm going to apply a fixture here and a load here, and I'm going to essentially watch this thing deflect. Now, where does the 2D simplification part come in? Now, if you notice, this is just a piece of extruded geometry and it's quite thin. So I can actually make the plane stress assumption and run just the analysis on this surface without actually having to run the analysis on the three-dimensional geometry. So in order to set up a 2D, in order to set up that 2D simplification, I'm going to check that little 2D simplification button, select the analysis type that I want to run, and I'm going to hit the green check mark. Now that brings me to another window. Now this is where I have to take a call on what kind of 2D simplification I'm going to execute. Is it the plane stress? Is it thin geometry? Is it plane strain? Is it a geometry with a infinitely long extrusion length? Or is it axis symmetric? In our case, it's going to be plane stress. The only other input I need to give the software is the plane to essentially extract the two-dimensional geometry. Now once I have the plane extracted, I need to specify the section depth, which is about 0.75 inches in this case. Awesome. So once I have that selected, I have similar, the simulation feature tree that I'll have to specify the material properties and that I can use to specify the material properties, the boundary conditions, and the mesh for. Um, as far as the material of the crane goes, I'm just going to assign a plain carbon steel. Here the material doesn't really matter because I'm assuming linearity, and B, I'm only going to study the stress distribution. If I look at displacements, will the material really play a big role? But if it's just a stress distribution I'm studying, the kind of material I choose should not affect the analysis. Now, as far as how this thing is fixed, I'm going to assign a fixed geometry to that little face or that little edge. Now, making this plane stress assumption inherently constrains this little two-dimensional piece from moving in the z, so you do not have to worry about what happens in the z direction. You only have to apply the boundary conditions in plane. Okay, now that I have the fixture assigned, I only need to introduce the 5,000 pound load. If you notice, the 5,000 pound load acts along the edge and is not distributed along the curvature. So in order to do that, I'm going to hit the selected direction. So that automatically lets me select a point. Now, if you're not able to grab the point, you can use the G key to kind of zoom into that point. Now, once you have the point selected, by default, the plane that you use to define the two-dimensional geometry will be used as a reference. Now, since it's the front plane, the X and the Y orient with respect to these icons orient with respect to the X and the Y. I'm going to apply the 5,000 pound load. Change the unit system here in the Y direction. Great. Now, once I have that assigned, I'm going to mesh the model. There are different kinds of meshers. I'm going to use the blend curvature-based mesher, and since I do have two-dimensional, I'm only running an analysis of the two-dimensional geometry. I can get a little adventurous by increasing the mesh density. And I'm going to run the analysis. Now, what I'd like to see is essentially the y direction of stresses along that edge, because that's what I'm going to validate through hand calculation. So I'm going to right click stress, I'm going to hit edit definition, and I'm going to change up this definition to reflect what happens in the y direction. And since most of my calculations are in PSI, I'm going to change the unit system to PSI as well. Okay, great. Now this tells me a whole lot on what are the boundaries of the stress distribution. Let's see. I'm going to set this to KSI. What are the maximum minimum? But if I actually wanted to look at what the stress distribution is at that edge, what I can do is I can grab the probe tool, hit on selected entities, grab that edge so the edge is highlighted, and I'm going to hit update. So this populates the stress distribution along that edge on, or this populates the stress values of every node that lies on that edge. Now, if I'd like to see a graphical representation of this, there you go. Now, I kind of want to compare this result to hand calculation, so I'm going to jump back to the software. Now, before I jump back into the presentation, uh, I'd want to show you that, if you like to shove this in the presentation and to, you know, and actually see how the three-dimensional geometry behaves, you can actually, get the output with the stress distribution displayed along with the three-dimensional geometry. Great. Now, now that we've run a basic stress analysis and figured out what the stress distribution is in KSI, I'm going to jump back to the presentation to kind of walk you through how I run this process analytically. Now, as far as hand calculations go, is this is a curve. This can be considered a curve beam. So I recommend reading articles on stress analysis of curve beam just to understand this process. But if I can summarize this process, now this is essentially the system that we need to figure out the stress distribution for. Our goal is to study the stress distribution or the stress in the y direction along the line A and B. Now there are two contributions to the stresses. One contribution is just the tensile load. The second contribution is the moment by virtue of the 5,000 pound force. Now, while The tensile stresses, by virtue of the 5,000 pound forces, are easy to calculate. The bending stresses can get a little applied and requires a little background on curved beams. Now, what each of these variables stand for are, so the first line of calculation is essentially to figure out where the neutral axis of the curved beam are. Now, the principal differentiator between straight beams and curved beams are that the centroid and the neutral axis for a lot of straight beams lie in the same point, lie along the same line. So neutral axis is where the fibers don't undergo any stresses. So uh, there are, for specific cross sections, there are certain formulas that help you estimate what the neutral axis is. Now the neutral axis formula for a square cross or a rectangular cross section is indicated by this first line. Now the eccentricity E is essentially the distance between the centroid and the neutral axis. And finally, M stands for the moment by virtue of the 5,000 pound load. Now the moment is calculated about the centroid. Now using this moment and specifying this moment as a function of R and the bending stress. Now varying this R from the inner fibers to the outer fiber, in our case from 2 inches to 6 inches, yields different stress distributions across the line AB. Now feel free to please feel free to take a screenshot of this slide and write to me if you have any questions about this. Great. Now as far as the results go, we got pretty close. We have about 15 psi with the simulation, and our hand calculations showed about 16 psi, while the tension side got really close. At the compression side got really close as well. Just goes to show that simplifying geometry does not sacrifice too much of the accuracy. It uh, with analysis, it's always common practice to cordon off areas that you feel are important to structural analysis and kind of simplify the geometry in order to maximize them, in order to get relevant results in the shortest amount of time. Okay, for my next case, I have a 3-point bend test. We've done another webinar that walks through how you set up a 3-dimensional 3-point bend test, but the 3-point bend test for certain geometry tend to be a plane stress problem. So I'm going to walk through how you can convert this kind of 3-dimensional geometry into 2-dimensional, into this 3-dimensional analysis into a 2-dimensional analysis. Now, the key here is that this will be a nonlinear analysis. So anytime you're trying to test the flexural strength of an object through a 3-point bend test, it undergoes large deflections that requires a nonlinear solver in order to run the analysis. Now, anytime you go into the into nonlinear finite element analysis, it involves a lot of steps and the analysis process can get time consuming if you aren't careful with the kind of geometry you're analyzing and the kind of constraints you're applying. So I kind of want to walk through that for the 3-point bend test case. So jumping back into the software, so you'll notice that there are a number of constraints that I've applied in order to stabilize this model for a 3-point bend. Because with the bend tests, essentially, there isn't an ideal constraint that this model has. The model is only constrained in between these rollers. So you need to figure out creative ways of stabilizing this that renders this 3-dimensional analysis a little tedious to run. So what I'm going to attempt to do is to run a 2-dimensional analysis, and I'm going to show you how I set up the 2-dimensional analysis. So to set it up, I'm going to start off by creating a new study. I'm going to select the nonlinear button. I'm going to hit the use 2D simplification again. Again, just a note, there are 3 analysis types that you can run with 2D simplification. They are the static, the thermal, and the nonlinear. Once I grab these analysis types, what I'm going to do is I'm going to select the kind of simplification I'm going to use. In this case, it will be plane stress. I'm going to grab the plane to generate the 2-dimensional geometry. And finally, I'm going to specify the extrusion depth. Now, once I have those defined, it's only a matter of applying fixtures. Now, as far as the way this thing is fixed, an essential fixture is to constrain the center to move only along the Y, because the assumption is as this thing is bending, all the fibers or all the grains that are distributed along this line do not move, essentially stay on the same line. So that's a way by which you can stabilize this in the Z direction. Now this is automatically stabilized in the Y direction by virtue of the contacts that we're about to design or define between the rollers and the bar. Now just walking through the fixtures, of course the bottom rollers are going to be fixed at the base, and the top roller is essentially going to have the prescribed displacement. So I'm going to grab the top roller and I'm going to assign a 2mm displacement. It also helps stabilizing this top roller in the Z direction. So now this thing has been instructed to move 2mm along the Y direction, and by virtue of the contact is going to bend this little bar. Okay, now the only thing that's missing are the contacts. So as far as the contacts go, we can create local contact sets between each of these entities. So ensure that you have the sliding contact set selected and grab all the edges that are about to participate in this deflection process. So that's one contact set. In the same fashion, I'm going to define the contact set between the top roller and the beam, and the bottom roller and the beam. So I have these contacts already set up. So what I'm going to do is I'm going to save some time and I'm going to copy those contact sets into the existing analysis. Okay, great. The only other thing that's left to do is to create a mesh and run the analysis. I'm going to use a blend curvature based mesh and I'm going to set the size to 1mm. Okay, once the analysis mesh is ready to go, I'm actually going to copy in the material properties too. It's mostly alloy steel and I have a custom material property defined for the material of the beam. Now with nonlinear analysis, since the analysis is being solved in steps, you're able to see the results update as it undergoes this entire 3-point bend process. Now what we're again interested in is the flexural strength or the flexural stress in the Z direction. So I'm going to switch the plot to SZ. Now with hand calculation, it was determined that we had about 3.18 megapascals, and this came pretty close. And the time it took to run this analysis is about 14 seconds. Again, demonstrating you can get a whole lot of insight by simplifying your geometry, and you don't necessarily have to run an analysis on the entire model all the time. If you can think of creative ways for simplifying geometry by taking advantage of some of the tools that's built into the simulation software, it's going to save you a whole bunch of time, and it's going to help you run multiple design iterations till you find that one design that you're satisfied with. So just a comparison between the 3-dimensional and the 2-dimensional study. Well, the stresses came pretty close. Through hand calculation, it was about 3 megapascals at the bottom, at the outer fibers. Now the time taken for the 3-dimensional analysis run was about 10 minutes 41 seconds. And finally, the time taken for the 2-dimensional analysis to run was about 31 seconds. To wrap this presentation up, now these kind of simplifications help you really explore your design space. Now by combining this with the structural design optimization tool, what you can do is you can automate the structural optimization of your geometry. For instance, in this case, let's consider this as a piece of metallic cheese. You want to vary the size of each of these holes, and you want to make the holes large enough to minimize the geometry, but without compromising the structural strength. Now, how do you set up such a problem in analysis? I'm just going to jump into the software and walk you through some of the steps. So this is the initial geometry, and this is the stress distribution. We have about 18 megapascals now, indicating that we have a lot of room to play for this specific material. The failure point is about 40 megapascals. Now, what we can do with analysis is to utilize design optimization tool that's built in to automate the variation of these hole sizes to come up, like I said, to come up with geometry that minimizes mass but maximizes strength. So in order to access this design optimization tool, you can jump into the Evaluate tab and grab the Design Study button. Once you grab the Design Study button, it's a three-step process. You specify all the variables that changes. You specify the rules. In this case, it would be to maintain the stress distribution of the model below a certain value. And finally, you input the goal for the analysis. Now, again, the goal here would be to minimize the mass of this model. Now, as far as the variables go, I have these variables predefined. So if you notice, I have this little parameter definition box. When I select each parameter, these parameters kind of highlight. I can even create new parameters by selecting a new row and just grabbing a dimension off the screen, and which automatically updates. Now that I have all these parameters defined, all I need to specify to the software is a range. So its the initial hole size is about 20 millimeters. I'm going to vary this so that the max to a maximum of about 40 millimeters. Or let's say 45. So in the same fashion, I input the different ranges. For the 4 parameters, and the analysis tool is going to run different permutations or different combinations of these parameters to figure out a distinct combination that minimizes mass and maximizes strength. Now once I have these variables in, now as far as the constraint goes, I can specify sensors that monitor the stress distribution of this model. Now all I need to make sure is that the sensor reads an output of 40 less than 40 megapascals for any combination of these inputs. And finally, what is my goal? My goal here is to minimize the mass. Since this is a two-dimensional analysis, while setting up the goal sensor, if I jump into the Evaluate tab, you'll notice that you can't pick mass properties for a two-dimensional model. So instead, you can actually grab the measurement and grab just the area of the model. So minimizing the area automatically minimizes the weight of the model. So once you have that measurement in, you can either choose to minimize, maximize, or set it to exactly a specific value. And after that, you hit the run button. We've run a little bit over time. This analysis takes about 40 seconds to run, and it sweeps through about 27 different iterations. Now, just to give you an idea of what this design space looks like, here is the optimized study. So if I grab the optimal iteration, you can see all the geometric values update to the model, and you can see the stress distribution between the difference in stress distribution between the initial and the optimal. So with the optimal configuration, the hole size were increased, and the stress distribution was as close to our limit, which is about 37 megapascals, and that of course uh, ups the displacement a little too. Now you have access to every iteration. Suppose you'd like to see the iteration that actually failed. You're able to see where that failure is and uh, the combination of geometric parameters that essentially caused uh, this to fail our criteria. Yep, and that's about it, guys. So as a quick summary, what we went through in this little presentation is how can we utilize the integrated structural analysis tools in SOLIDWORKS to give us quick insights into the structural strength of our designs. We took a quick peek at a linear and a non-linear analysis as well, the linear analysis being the crane hook and the non-linear analysis being the three-point bend test. Well, we also ran an analytical validation, an analytical calculation, comparing the results between SOLIDWORKS simulation uh, and hand calcs for the crane hook. And finally, we looked at how we can take advantage of the design optimization tool to kind of explore our design space to give us ideas of what kind of simplifications you can make to your model without compromising its structural strength. Well, thank you for joining me on this webinar this afternoon. If you have any feedback, please don't hesitate to write to us or give us a call. We'd be happy to incorporate any feedback you have into our future webinars. Now I'll open the floor for questions. Thanks, guys. Have a great day.